Good morning to all. I am Dr.P. Kalaivani, Assistant Professor of Chemistry, Nirmala College for Women, Coimbatore. In this module, we are going to discuss about absorption and intensity shifts in electronic spectroscopy. First, we start with fundamentals of electronic spectroscopy. Spectroscopy is the study of interaction between electromagnetic radiation with matter. What is electromagnetic radiation? Electromagnetic radiation is a form of energy that is transmitted through space at an enormous velocity. The entire range over which electromagnetic radiation exists is known as electromagnetic spectrum. It covers an immense range of wavelength. This is the diagrammatic representation of electromagnetic spectrum. If we arrange all types of electromagnetic radiations in order of their decreasing wavelength, then the portion below the visible region is called IR, while that above it is the UV region. IR radiation have longer wavelengths and are thus less energetic. Cosmic rays carry high energy while radio waves are least energetic. Microwaves have larger wavelengths and are used in telephone transmission. Out of all, here we are focusing UV visible spectroscopy. It involves the promotion of electrons from the ground state to higher energy state. Hence, it is also called as electronic spectroscopy. It is used for the qualitative and quantitative analysis of chemical species. Let us discuss theory of electronic spectroscopy. When the molecule absorbs ultraviolet or visible light, its electrons get promoted from the ground state to the higher energy state. In the ground state, the spins of the electrons in each molecular orbital are essentially paired. In the higher energy state, the spins of the electrons may be paired or parallel. If the spins of the electrons are paired, it is called as excited singlet state. If the spins of the electrons are parallel, it is called an excited triplet state. The triplet state is always lower in energy than the corresponding excited singlet state. Therefore, triplet state is more stable as compared to the excited singlet state. In the triplet excited state, electrons are further apart in space and thus electron-electron repulsion is minimized. Normally, the absorption of ultraviolet or visible light result in the singlet ground state to excited singlet state. That is, excitation proceeds with the retention of spins. An excited singlet state is converted to excited triplet state with the emission of energy as light. The transition from singlet ground state to excited triplet state is symmetry forbidden. The higher energy state are designated as higher energy molecular orbitals and also involves the promotion of one electron from HOMO, that is highest occupied molecular orbital, to the lowest unoccupied molecular orbital LUMO. In most of the cases, several transitions occur resulting in the formation of several bands. UV spectrum is a record of the amount of light absorbed by the sample as a function of the wavelength of light in millimicron or nanometer units. Its range is from 200 to 800 nanometer. 200 to 400 nanometer is called as ultraviolet region and 400 to 800 nanometer is called as visible region. Lambert's law and Beer's law are the two absorption laws which govern the absorption of light by the molecule. According to molecular orbital theory, when a molecule is excited by the absorption of energy, that is ultraviolet or visible light, its electrons are promoted from a bonding to an antibonding orbitals. There are four types of transitions exist in electronic spectroscopy. When sigma electron is promoted to antibonding sigma star orbital, it is represented as sigma to sigma star transition. When non-bonding electron gets promoted to an sigma star orbital, represented as n to sigma star transition. Similarly, Pi to pi star transition represented promotion of pi electrons to an antibonding pi star orbital. When an n electron is promoted to pi star orbital represented as n to pi star transition. Among them, sigma to sigma star transition requires more energy. It is a high energy process since sigma bonds are in general very strong. The organic compound in which all the valential electrons are involved in the formation of sigma bonds do not show absorption in the normal ultraviolet region, that is from 180 to 400 millimicron. For saturated hydrocarbons like methane, propane, etc., absorption occurs near 150 millimicron. Consider sigma to sigma star transition in a saturated hydrocarbon. Such a transition requires radiation of very short wavelength, that is in high energy. The energy required for various transitions obey the given order. It starts from sigma to sigma star. The next one is n to sigma star transition. This type of transition takes place in saturated compounds containing one heteroatom with unshared pair of electrons. Some compounds undergoing this type of transitions are saturated halides, alcohols, ethers, aldehydes, ketones, amines, etc. Such transition require comparatively less energy than that required for sigma to sigma star transitions. Third one is pi to pi star transitions. This type of transition occurs in the unsaturated centers of the molecule, that is in compounds containing double or triple bonds and also in aromatics. Last one is n to pi star transition. In this type of transition, an electron of unshared electron pair on heteroatom gets excited to pi star antibonding orbital. This type of transition requires least amount of energy out of all the transitions discussed above and hence occurs at longer wavelengths. Example, saturated aldehydes. This slide shows the instrumentation of spectrophotometer. It is a device which detects the percentage transmittance of light radiation when light of certain intensity and frequency ranges passed through the sample. Thus, the instrument compares the intensity of the transmitted light with that of the incident light. The modern ultraviolet visible spectrometers consist of light source, monochromator, detector, amplifier and the recording devices. The most suitable sources of light are tungsten filament lamp and hydrogen deuterium discharge lamp, which cover the whole of the UV visible region. One of the beams of selected monochromatic light is passed through the sample solution and the other beam of equal intensity is passed through the reference solvent. The spectrometer electronically subtracts the absorption of the solvent in the reference beam from the absorption of the solution. Hence, the effects due to the absorption of light by the solvent are minimized. In this way, the absorbance or the transmittance characteristics of the compound alone can be measured. The signal for the intensity of absorbance versus corresponding wavelength is automatically recorded on the graph. The spectrum is usually plotted as absorbance A against wavelength lambda. The plot is often represented as E epsilon maximum. It is extinction coefficient against wavelength. When the sample absorbs light, its intensity is lowered. Thus, the photoelectric cells will receive an intense beam from the reference cell and a weak beam from the sample cell. This results in the generation of pulsating or alternating currents which flow from the photoelectric cells to the electronic amplifier. The amplifier is coupled to a small servometer which in turn is coupled to a pen recorder. Thus, it records the absorption bands automatically. Actually, the amplifier is coupled to a small servometer which drives an optical wedge into the reference beam until the photoelectric cell receives light of equal intensities from the sample as well as reference beams. Absorption and intensity shifts of electronic spectrum result four types of effects. Among them, bathochromic and hypsochromic shifts are due to absorption shifts. Hyperchromic and hypochromic effects caused by intensity shifts. This may be due to the presence of oxochrome or chromophoric groups. This slide explains bathochromic shift or redshift. The absorption maximum shift towards a longer wavelength is called as redshift. It is due to the presence of an oxochrome. What is oxochrome? It is a color enhancing group. By the introduction of oxochrome or decrease the polarity of the solvent, redshift will be occurred. We consider benzene, its lambda max value is 255 millimicron. Now we introduce an oxochrome, that is NH2 group, which results aniline with the lambda max value of 280 millimicron. This is because the lone pair of electron on nitrogen which enters into resonance conjugation with benzene ring. This leads to extended delocalization of electrons, hence lambda max value get increases. Hypsochromic shift or blue shift. Lambda max value is shifted towards shorter wavelength. It may be caused by the removal of conjugation and also by changing the polarity of the solvent. In the case of aniline, absorption maximum occurs at 280 millimicron because the pair of electrons on nitrogen atom is in conjugation with the pi bond system of the benzene ring. In its acidic solutions, a blue shift is caused and absorption occurs at shorter wavelength. In anilinium ion formed in acidic solution, the electron pair is no longer present and hence conjugation is removed. Hyperchromic effect. It is an effect due to which the intensity of absorption maximum increases. That is, epsilon max value get increases. For example, pyridine. It occurred at 257 millimicron and epsilon max value 2750. It is shifted to 262 millimicron with the epsilon max value of 3560 for 2-methylpyridine. The introduction of oxochrome, that is methyl group, in the second position of pyridine usually increases the intensity of absorption. Hypochromic effect. It is defined as an effect due to which the intensity of absorption maximum decreases, that is epsilon max value decreases. The introduction of group which distorts the geometry of the molecule causes hypochromic effect. For example, biphenyl absorbs at 250 millimicron with the epsilon max value of 19000, whereas 2-methyl biphenyl absorbs at 237 millimicron with epsilon max value of 10250. It is due to the distortion caused by the methyl group in 2-methyl biphenyl. The same kind of effect also observed in naphthalene and 2-methyl naphthalene. Finally, we conclude in this module we have discussed about fundamentals of spectroscopy, that is electromagnetic radiation, theory of electronic spectroscopy, types of transitions, instrumentation of UV spectrophotometer, and absorption and intensity shifts in electronic spectroscopy. Thank you.